Back in 90s, internet speed was terribly slow. Someone can even remember how they turned off loading images in exchange to improve page loading speed. And what now? Nowadays speed increased drastically, 100 times faster. For now, speed enough to fulfill all our demands. Even things such as downloading Warzone or Fortnite is just a matter of 30 or 60 minutes, if you're lucky enough to live in a country with a proper connection, which is strangely not the case in most of Europe. But that's only for now. In the nearest future, with all this rising demands, it definitely wouldn't be enough. So let's find out what the theoretical and practical limits for the internet connection. Currently, the fastest internet connection is 31 km or 18.6 mile optical fiber inside Japanese research facility. In November of 2023, they achieved insanely speed of 484 terabits per second. At this speed, you would be able to download the 3 copies of whole Netflix library in less than 1 second. That's really some hilarious numbers. It's really incredible how much information can pass through an optic fiber, no wider than a human hair. All of this is very impressive, but realistically it's only under the lab condition, and on a practice the fastest internet connection at everyday life is transatlantic cable Marea. It contains 16 fiber, which provides total speed of 200 terabits per second on each cable. Okay, let's get to the main question. Is there any real possibility to increase speed endlessly? Let's look how it works. Each 1 and zeros encodes to a different level of signal on a line. Every impulse is a clock speed. From this, we can form 3 main ways to increase speed. First, we can lower longevity of each impulse. In other words, just increase clock speed. That's exactly the same what you do when overclock CPU on a PC. In this way, we raise the volume of data at each second. Secondly, there are plenty of room to increase count of levels of impulse. So at each impulse we will send not 1 but 2, 3 or 4 and even more bits, depends on the count of levels. And the third one is to increase the amount of wires inside every cable. And as always, here is plenty of obstacles on the way. We will look only at wire connection, as even 5G hardly struggling to beat wires, so there is no point to look at Wi-Fi and cellular network. Need to mention that Wi-Fi 6E make a good step up front, but still limited by short wavelengths and kinda have a harder time traveling long distances. Anyway, there are no intentions for wireless network to overpower a wired one. To begin with, we will start with usual copper wires. A constantly changeable signal inside copper wires is nothing less than AC current. So the more clock speed of AC current, the more speed and as a result more waste of energy, like a heat. For example, RJ cable category 8, which is currently top of the line, is defined up to 2000 MHz, but only for a distance of 30-36 meters or 98-120 feet respectively. Suitable for home usage, but nothing more than that. For instance, original category 7 cable was capable of transferring 10 gigabit network over 100 meters on 600 MHz. As you can see by this example, by raising the frequency we eventually lower the distance, and it's really hard to determine signals among noises. But that's not the only reason, as if you will push frequency further, you will face up with skin effect. To keep it short, it is tendency of altering current inside conductor and distribute most of it on surface or even on a wire shielding, which, as you can guess, also will reduce possible length of a cable. Okay, the frequency is the real hard one, but what about levels? Here is also a catch, as a signal can be clear and easy to read only at input, and on output it all messed up, as it take too much yesterday. All of these consequences of distance and noises. Do not worry, it's easy to fix and define actual signs, but only if there were only a couple of levels. This increases numbers of levels become more difficult to properly identify them. For example, a 10 gigabit spec contains 16 discrete levels. To contain all of these levels in order, those wires use huge amount of shielding and the best quality of copper. In theory, we can keep moving in a way of increasing levels, but costs for each meter or inch will be high enough to make them unaffordable. And what about increasing the number of channels? Let's be honest, in a world where everybody wants to get off from cables as much as possible, have a good luck to convince people of having 2, 5 or even 10 times thicker cable. For cooperative solution and transatlantic connection, it's a reasonable way, but also in the cost of higher price. So we really have to push copper wires to their limit, and they are not enough even for nowadays. So what will be next? The higher speed can only provide an optic fiber. The fiber optic technology is based on a physics phenomenon also known as a total internal reflection. If we will target the laser beam on a glass, some part of beam will always be reflected and another one pass through a glass. The ratio of reflection depends on a beam degree related to glass surface. Something similar will happen if put laser on the other side of a glass, but by passing critical degree it will become fully reflected and nothing will come outside. So, creating an optical waveguide allows us to transfer light through countless reflections along without any visible losses. The standard fiber cable has losses around 5 to 10% on a distance of 1 km or 0.6 mile. In compare with copper wire, it looks like nothing. So in a fiber we can achieve some really insane speed. Is it right? As always, there are also some catches. Different parts of light beam inside fiber cable can pass under different degree, have different count of reflection, and pass different distances. As a result, they will reach destination not simultaneously. It can lead to some uneven signal or even interfering with closest impulses. It's a main point why fiber clock speed is limited to a couple of thousand MHz. And yet still it easily overpowers copper wires, which is more than enough for the end user. Luckily for us exists a single-moded optical fibers. Their main advantage is size. They are so tiny that core is measured only 8 to 9 micron. It allows them to pass light nearly one solid way, so they doesn't have this uneven signal at output, which leads us to even greater speed than usual optic fiber and higher volume of data. And as always, in a cost of higher price. Need to mention that costs not only for a fiber itself, but for the whole equipment as a transmitter, receivers and etc. Can deny that it's very unusual to see a smaller thing being capable of transfer bigger amount of data than a thicker one. And even here we have some theoretical limit of bandwidth, which properly described in Shannon's theorem. On the practice, currently hard to beat bandwidth is 36 terabits per second on a distance around 1000 kilometers or 700 miles, or around 26 terabits per second and a transatlantic connection. There are a couple of solutions on how to pass the increased amount of data. We can simply transmit light with the different wavelengths in a single cable and practically they will not interfere with each other. Even nowadays, it's uncommon to use a couple of hundreds of wavelengths in the same cable. Each of them is a separate channel of data. Thanks to tiny size of fiber, it's easy to group couple of them inside one cable without drastically increasing the size of it. Each of these aspects can be increased endlessly, but to be honest, even for the nearest future that seems like more than enough.